Hey there, it's week 11 and we are going into exam week again. So this we're going to be doing the second exam this week for the first part of the week. And then just like with the first exam, in the second half of the week, we will go ahead with our uh, usual quiz and discussion questions, but we won't have a your turn or a constellation question this week. But I do want to just point out that this is a good time to get caught up. So as you're studying for the exam, since one of the best ways to study for it is to work on assignments, go ahead and do any of those assignments that you missed, or go ahead and do or make corrections on any assignments that need that. This is really the time. You could see similar questions show up on the exam, so you really want to make sure you've got you're ready for whatever I'm going to throw at you here. So I'm going to focus today on the exam, and what I want to do is start by just letting you know how it works. The short answer to that is very much like the first exam. So just like the first exam, there's going to be a set of multiple choice questions. There's 10 of those, and then 3 written answer questions. And those questions will be set up as I say, very much like the first exam, where you'll have one that's kind of like a discussion question where you have to describe some of the ideas in the course. There will be one critical thinking question where you have to apply the ideas to a situation that you maybe like, but not exactly the same as you've seen before. And then there will be a calculation question. And the calculation will be based on a constellation file that will be given with the exam. So practicing any of these, whether it's constellation questions, your turns, quizzes, discussions, I mean, that's really a big part of how you want to prepare for this exam. Now, this exam covers the material since the last exam. So that means starting with telescopes and the sun, working through basically all the material on stars and on stellar evolution. So you're going to be seeing things that deal with the basic properties of stars, things that deal with our sun and its structure, how we use telescopes, and of course, the different steps in the life of a star. So that's what you want to be preparing for this exam. The other thing to mention is that this is an open book, open notes exam. You will be given 2 hours to do the exam, but you should really prepare for it the same way you would prepare for a closed book exam. You should be studying like you weren't going to be able to look up everything, because you don't want to spend all your exam time looking things up. You want to spend the time on the exam focused on answering the questions that you know, and then if you have to look something up, you could do it. But you don't want that to be what you're doing for all the questions. So make sure you're ready for most of what I'm going to give you. And then if you have to look something up, you have that option. Now, the other thing to mention is that since it is open book, I know there's always tempting to just kind of look up the answer somewhere. But remember, I want you to write the answers in your own words. So don't just copy what I said or copy what you see it on some website. Because if you do that, I'm going to take those points off. That's not good. That's not good. I want to see what you understand, not what somebody else understands. So make sure that you answer that way. You answer with what you know. So let's. Oh, and one other structural thing I should mention here about the exam. With the calculation question and possibly one of the other written answer questions, you might you'll have it'll be set up so that where you'll make sure you'll do your own answers on your own computer or on paper, and then upload those as a file. If you got one of those file upload questions and somehow you hit a technical problem, it's just not working. Something you can't get the file to go, whatever. Send it to me. Just send it to my inbox and do that right away. Don't wait around. Um, uh, I'd much rather get your answers, get them sent into me, and let me know if you had a problem. That's fine. But I don't want the technology to be the reason you have a problem on the exam. And in fact, that's generally true. If for some reason there's a technology problem that's keeping you from doing as well as you should be on the exam, let me know about that. And if you have to send me your answers directly, you can do that. I want you to. I don't want that to be your problem. I want you. I want you to be able to answer based on what you know. Okay. Well, let's take a look at the big topics then. As I say, this exam starts with the telescopes chapter, and so that was a short chapter, so that means you're not going to see a lot of questions from that, but there's a few key ideas, right? There's a few things that you definitely want to understand. You want to understand those basic properties of a telescope. You want to understand things like how does aperture affect the telescope? Okay, what does that mean? How does that what does that do your telescope? Um, you're observing the instrumentation. Okay, you want to be able to talk about different types of instruments, whether it's imagers or photometers. Um, you should certainly also be able to talk about how the observing location affects what you're doing, as well as the part of the spectrum. Okay, what are you observing in radio? Are you observing visible light? Are you observing gamma rays? Right. Each of those has their own things they're good at observing, but also each of them has their own limitations, things you can and can't see it can't do with them. And so, things like, gamma rays you can't observe from the ground, right? They just don't make it through our atmosphere. That's the kind of thing I want you to make sure you understand. Um, and so, for example, a critical thinking question I might give you from this chapter would be something like the ones we did in the year term question, where you have to look at, I give you a couple of different telescope projects, and you should decide, well, what are the strengths and weaknesses for each? And you should be able to talk about both strengths and weaknesses for both ones. Okay, I don't want to say this one's all strengths and this one's all weaknesses, because believe me, they're not. Okay, there are pros and cons on all. Okay, the next chapter was the chapter about the sun. And first thing to appreciate is the sun is a star. It's an ordinary main sequence star. So all the stuff that we say about the sun in this chapter applies generally to main sequence stars. Okay, it's a big ball of hydrogen, right? It's uh, got this balance of pressure and gravity that defines the structure of the sun, and it has heat that can flow through either through radiation or through conduction or convection. In the case of the sun, it's convection and radiative diffusion. Conduction doesn't do very much there. And of course, it's powered by by nuclear reactions. And so you should certainly have at least that basic picture. Okay, what is the reaction that powers the sun? Take four hydrogens, throw them together, it makes helium, and it releases a lot of energy. The reason it releases that energy is because the helium has a little less mass than the four hydrogens that go into it. And that difference in mass is the energy that is produced. So that's that E equals mc squared that we've used here now a couple of times. So this is one where I might ask you for something like to go ahead and talk about, well, how would the sun change if we change the conditions? Okay, we did a question like that where we talked about how the sun's mass changed. So what and mass is a big one. If I'm going to change something, that's the most important one, because just about everything else is driven by a star's mass. So that's the kind of thing you might look for that. Okay, then we got to the stars, and really the whole rest of this last couple of months has been about stars. So we talked about those basic measurable properties of stars. What can we measure directly? We can measure the distance. We can use parallax. If we know the absolute magnitude, we can measure we can measure distance by comparing apparent and absolute magnitudes. So we looked at both of those in both lectures and labs. A lot of folks now have done labs that use that too. And so uh, you want to know what the magnitudes mean. You want to know what the difference is between apparent and absolute magnitude, and you certainly want to be able to calculate distance either using parallax or using magnitudes. And I could throw either one of those at you here. So you should be able to look at something like a constellation table and calculate distances that way. We also talk about temperature of stars, and this is what gets us into those spectral types, those O, B, A, F, G, K, M. And yes, you really should know that list, that sequence of letters, because uh, it really is something very fundamental to the way we classify stars. So we talked about about how we measure the temperature of stars. There are several different ways. We did that back in the first part of the course, where we used the peak wavelength. Another way you can get a star's temperature is by looking at the absorption lines in the star. And there's one of the lab options that folks have been doing actually has you doing some of that. But that sequence, that OBAFGKM, is a temperature sequence from hottest to coolest stars, or if you like, from bluest to reddest stars, because the blue stars are the hot ones. And that then leads us to the HR diagram. And you've seen a lot of HR diagrams now. That's become kind of a very common thing. You should probably be able to just draw up an HR diagram without even really thinking about it by now. And if you can't do that, that's a good thing to practice, because I'll tell you right now, looking further ahead on the final exam, I have as a standard question that everybody has to answer is draw and label an HR diagram. So looking forward. So you want to make sure you've got that down, because I'm gonna you're gonna get a question like that, not necessarily on this exam, but definitely on the final. So you should certainly be comfortable with an HR diagram. You should know what it's telling you, and know about the different types of stars, because this is a good way for us to classify stars based on where they are on that diagram. And connecting those to the luminosity classes, right? Those Roman numerals that we put after the spectral type. That's Those are really important to get a sense of. In a sense, that's the vertical part of that HR diagram. So you've got your white dwarfs, which are don't really fit, don't really have a luminosity class. They're kind of all by themselves there. But then you've got the main sequence, that's the class 5, the subgiants, the giants, the bright giants, and then on up to the supergiants right at the top of the HR diagram. Those are the ones that have that have the most luminosity. And then, as we saw a little later on, they represent the end stage for the higher mass stars. But you should have a good sense of what those different types of stars are, what's different about them, how we can tell that a white dwarf is a dwarf, right? What are we looking at there? What tells us that it has to be small? All right, well, because it's really hot and it's not very bright. That's a key combination. That means it's got to have a small surface area. So we looked at at these different types of stars, and we also talked then about the lifetimes of stars, and we did that in conjunction with talking about star clusters. So a cluster of stars, a group of stars that all form together and they stay together for some portion of their lives. And um, this ties it, and we know that from looking at our calculations of how fast stars live, that the big stars, the high mass stars, the ones that are many times the mass of the sun. I'm not talking about whether giants or supergiants. I'm talking about just main sequence stars with a lot more mass than the sun. They have really short lives. They die off pretty fast. The stars with a very low mass, those red dwarf stars that have very low luminosity, because they have low luminosity, because they're using their fuel very slowly, they run out. They run out of fuel, or rather, they hold on to their fuel for a very, very long time. So the universe right now is not old enough for a red dwarf to have died yet. That's how that's how long they last. So the red dwarfs have these ridiculously long, trillion-year lifespans for the lowest mass ones. So our sun has about a 10 billion year lifespan. And one thing you want to make sure you're clear about, there's a difference between lifespan and age. Our sun is about 4.5 billion years old, right? That's how long ago it formed. But its lifetime is about 10 billion years. Okay, so that's how long it's going to last, at least as a main sequence star, about 10 billion years. So it's nearly halfway through its life right now. Getting back to star clusters, when we look at a star cluster, we're looking at stars with uh, uh, different masses that all formed at the same time. And so if you look at the HR diagram for one of those, in fact, let me bring up an HR diagram here so we can look at it. There we go. There it is. Okay, so when we see an HR diagram like this, there's your main sequence. You've got the giants and the supergiants above that, the white dwarfs down below. Just looking at the main sequence part here, okay? You've got all these stars of different masses. The low mass stars down here, they have the really long lives. High mass stars are up here, they have the really short lives. So when a star cluster forms, it might have all of these, everything on the main sequence. But over time, the ones up here are going to die out first. And so over time, that main sequence is going to get shorter and shorter and shorter and shorter, because the ones up here, they're going to go. They're going to go. We'll talk about what happens to them here in a few minutes, but they're going to slowly die off. The ones down here, they're just going to sit around. Okay, the cluster started with them, and it'll keep them, and they'll just sit and sit and sit, and not much is going to happen to them because they're there and they don't change. There are hardly any change over billions of years because they use their fuel so slowly. Now, our sun is kind of in the middle, okay, as a 10 billion year lifespan star. It's a one solar mass star. So that means that if the sun formed in a star cluster and it stayed there, then it would stick around as a main sequence star in that star cluster for about 10 billion years. It would only change very marginally in that time. And then after that 10 billion years, it would suddenly go up and become a giant and so on. And we'll look at all that here in just a few minutes. But up until that point, it's kind of just sitting right here. And that's what it does for most of its life. Okay, so that's the properties of stars. Then we moved on and looked at star formation and stellar evolution. And so this is where we really get into how stars change, how they evolve. And we start out with a really key idea. Okay, we come back to that whole stars are a balance, right? Pressure's pushing in. Okay, gravity, I should say, is pushing in. Pressure's trying to push it all apart. And a star is always about the balance of those two things. So, what determines the pressure inside is how much heat it's producing. Okay, how much energy is it generating? So, the changes in the life of a star are mostly about how the energy generation is changing. So when you look at that, and in this section, we keep talking about, okay, well, what's going on in the core? Where's the power coming from? Where's the energy coming from? Because as that changes, that's going to change that balance of pressure versus gravity. And so what happens down in the core can make the star swell up or shrink down. And so most of the life of the star is all about things happening way down at the core, changing what happens out at the outside that we can see. So we started with star formation, and we looked at the stages of star formation, the types of stars that form. Stars form in these big molecular clouds, these big clouds in the interstellar medium, the dense regions where you have enough dust and gas that gets together that it can start contracting in on itself through its own gravity. So that's what's happening in here. Each of the little points and lots of places inside this big dusty cloud are places where a star is forming. And so there are probably tens of thousands of stars that are forming inside this cloud even as we look at it. So the cloud starts out as this big fluffy cloud of gas and dust, and it contracts in on itself. It gets smaller and smaller and smaller. It's effectively falling in on itself, and so it turns that it turns that gravitational potential energy that it has because things are far apart into heat, into kinetic energy, and then heat as it falls in. Just like when something falls here on the Earth, it turns gravitational potential energy into kinetic energy and then heat. That's what this is doing. That's what the cloud is doing too. Only it's not falling towards an object; it's just falling in on itself. And so that heats up the interior of the cloud. Eventually, it gets hot enough that it starts to glow. We call that a protostar. And when the core gets really hot, when the core gets up to the point where it's something like 15 million Kelvin, it could start fusing hydrogen. And so that's when it turns into a main sequence star. And so then the star enters the main sequence. It becomes, it goes into that sort of long middle period of its life when things don't change very much. They do change a little bit because as the star is going through the main sequence, it's changing, right? Because in the core, it's going through hydrogen fusion. It's turning hydrogen into helium. And that means over time, the composition of the core is changing. And so that means that the amount of pressure in the core changes because of that. And the core gets a little bit smaller and a little bit hotter, and the outer layers get a little bit brighter, a little bit bigger. Not a lot, but over the course of the sun's life, for example, it will change by about a factor 2 in brightness, okay, while it's on the main sequence. And that's why when you look at an HR diagram, the main sequence isn't just a really thin line, it's a band of things because not all stars are at exactly the same point on that in that light. And so even stars that are the same temperature can be a little bit different brightnesses. Well, then once that's great, that's that main sequence part of the life. And then what happens? Okay, at some point, all the hydrogen in the core of the star is going to get turned into helium. And once it's done that, you can't do hydrogen fusion in the core anymore. And so that's when the action gets started. The star at that point the core of the star, the inner part, is going to start falling in on itself again, and that's taking advantage of the other way that stars can generate energy, gravitational contraction. Okay, just like it did back at the start when it was a protostar. Again, the core is is creating energy by falling in on itself. And as it does that, it actually generates so much energy that it makes the outer layers of the star start to swell up. And you get an extra boost because some of the stuff just outside of the core, that the stuff that wasn't quite hot enough for fusion during the main sequence, well, that extra boost of heat pushes it over the edge so it can start going through fusion. So you have a contracting core, you have a shell outside that core where it's turning hydrogen into helium, where hydrogen fusion is going on, and then the outer layers of the star are swelling up. And of course, this is when it's a subgiant and it's on its way to becoming a giant star. And that process continues until the star gets till the core of the star gets hot enough that it can start fusing helium. And once helium fusion starts, then it settles down, right? It's almost like it's back on the main sequence again, only now instead of fusing hydrogen, it's fusing helium in its core. And so you've got this helium fusing core down at the center, but helium fuses at a much hotter temperature than hydrogen does. And so the star has to be a lot more luminous. Okay, it's got to be putting out a lot more energy, and that means it's much bigger. And so it's on the giant branch at this point. So it goes from subgiant fairly quickly up to giant branch, and then it sits down the giant branch for a while, about a tenth as long as it was on the main sequence, in fact. Now, this story is pretty consistent for pretty much all stars. So they all go through what I just described. But from here on out, the story changes depending on the mass of the star. And so whether we're talking about a low mass star, a high mass star, or a really high mass star, you're going to get a different sequence of events from here on out. The low mass stars, that's like 90 some odd, 99% of all stars are low mass stars. Okay, they are by far the most common stars in the universe. Our sun is a low mass star, so this is its story here as well. When it runs out of helium in the core, it goes through one more contraction phase. The core heats up some more. There, you get some you get a couple more shells of fusion going on. So you have a hydrogen shell and a helium shell, and then this contracting core way down at the center. But that contracting core never gets hot enough to go through the next stage of fusion. So that's it. That's as far as it goes. It kind of gets compacted down as far as it can go, and it stops. And that's it. In the meantime, the outer layers are, got all these different things happening down the core, are making the outer layers kind of unstable. And they start blowing layers of gas out into space. And that produces what we call a planetary nebula. And let me pull up one of those. I had it here a moment ago. Where is it? There it is. Okay, yes, I had this on earlier. So, a planetary nebula. This is a big shell of gas that's been pushed out by a dying star, a low mass star like the sun, the end of its life. So our sun's going to do something like this. There's going to be a few, in like 6 billion years, if you're in the right place, you'll look at the sun and you'll see something like this. The right place is not the Earth, by the way. The Earth will be gone by then. The Earth will have been toasted by the fact when the sun would turn into it was a giant star. So that's not the place you want to be. But so the sun will look like this. And as it's blowing away its outer layers off into space, the old core, right, that where all the fusion and all that stuff happened, it'll be left behind. And it'll be a little tiny dot right about there, and that'll be the white dwarf. And so a white dwarf is a cinder. It's the remains of a star that used to be a star like the sun, a low mass star, but it's dying off. And white dwarfs have a maximum mass of 1.4 solar masses. So that low mass star range, that goes all the way up to about 8 solar masses. But a star that's 6 or 7 solar masses, it's going to lose most of its mass in this. So the white dwarf that's left behind is much, much smaller than the star it started with. So that's the life of a low mass star. And then the white dwarf then just kind of sits there and slowly cools off. It takes billions and billions of years for that to happen, but that's all it's got left, right? There's no more fusion, no more gravitational contraction. It's just stuck. End of story. High mass stars, stars that are more than 8 solar masses, have a much more exciting life. I'll say there is a little intermediate mass range, and you folks saw that on the last constellation question, where they can actually get past carbon, but they can't get all the way to iron fusion. And so there's a small range there where slightly more interesting things can start to happen. But those are they still wind up as white dwarfs. They're just a little bit different composition like white dwarfs rather than the carbon oxygen ones our sun will do. Okay, but the stars that are more than 8 solar masses, they have the really exciting story. Okay, things start really happening for them because they can go beyond helium fusion. They can fuse carbon, they can fuse oxygen, they can fuse neon. Okay, and each time they fuse a new element at their core, they burn through that. They create a core that's made out of some heavier material like neon, and then that neon core has to contract. When the whole core is made of neon, it then has to contract again and go to the next thing, which is probably something like silicon, and then but eventually, after producing heavier and heavier elements through more and more layers of fusion, you get to iron. And iron is bad news for a star because you can't get energy out of iron fusion. So up to that point, when a star is going through those many different levels of fusion, it's going to be producing so is it having many different types of fusion going on in the core that have layers. You'll have a core fusion going on, and then a layer of one after another layer of lighter and lighter elements fusing as you get further and further out. All of that's going to generate so much energy that's going to make the outer layer of the star swell up till they're huge. Okay, so that's why these stars become not just giants but supergiants. So a supergiant star is one that's got many different types of fusion going on inside it at once. They're large. If you dropped a supergiant in our solar system, it would swallow out the entire inner solar system. Okay, it would be so much bigger than the inner solar system. It would go all the way out to Jupiter or Saturn. So those are stars that are huge. Now, remember when a star swells up to form a giant or supergiant, it doesn't increase its mass. The amount of stuff stays the same. It just gets spread out a lot more. So a supergiant is a very fluffy star. There isn't a lot of, especially the outer envelope, the outer layers of that are near vacuum. Okay, there's very little, it's a very low density thing overall. The core is really dense, but the outer layers aren't. So when a star swells up like that, you got to think of it as a great big puffball with a dense core down at the center. When, though, that fusion gets to iron, it makes this iron core. The star has run out of options. Okay, at that point, it's going to build that iron core until such time as the core's own, the physical properties of the iron can no longer hold it up against gravity. And at that point, that iron core then collapses in on itself. again, okay? Gravity always winds up winning in these things. So sooner or later, it comes down to the core contracting in on itself until you get, until it, until it turns into basically a giant atomic nucleus, okay? All the matter in the core, all the protons, all the electrons, all get turned into neutrons. And so you had this huge, dense ball of neutrons that is literally as dense as the nucleus of an atom. And when it comes down, it gets to that density, it bounces, and the shock wave from that bounce blows the star apart. And so instead of a nice gentle wind like this, what you get is a vast explosion. One of the brightest, most dramatic things that can happen in our galaxy. And so we call that a supernova. And let's see if I got a good supernova picture available here. Well, here's the remnant of a supernova. So this is the Crab pulsar. So when a supernova happens, when the star blows itself apart like this, that old dense core stays behind. And it's only a few solar masses. In fact, because it's turned to the whole core of the star has been turned into a ball of neutrons, maybe about 10 kilometers across. Okay, not very big, about a city-sized ball of neutrons. It's still got several solar masses, somewhere between 1.5 and 3 solar masses of stuff in there. Now, this is coming out of a star that started as 8 to 25 solar masses. So most of the star got blown away. There's just a little bit left behind, but that's the neutron star. And that's what's at the center of this supernova remnant. When that happens, if the star had any kind of rotation to it, the neutron star gets this huge spin. It spins 1,000 times a second. And it develops this very strong magnetic field that whips around and produces pulses of light, which is what we see, and that's what we call them pulsars. So when we talk about a pulsar, we're talking about a very fast spinning neutron star. So the core of an old, dead, high mass star. Now, this whole story about supernovas applies to high mass stars, stars that are at least 8 times the mass of the sun. Which means the sun ain't going to do this. Okay, the sun's going to make a planetary nebula and a white dwarf and have a nice quiet retirement, and that's it. Doesn't do this kind of thing. This is for the high mass stars. Except that I said this goes up to, this is for stars that started out as up to 25 solar masses. There's an even more extreme case, and that's when you have stars that are start out at more than 25 solar masses. Those stars have a really spectacular end, because when they die, the core contracts, the iron core collapses in on itself, just like we saw before. But in this case, it doesn't stop. So instead of stopping at the neutron star stage and bouncing out, instead it keeps falling. And there isn't much farther to fall at that point, because when you get that core too dense, when it's everything's packed too close together, gravity becomes strong enough that even light can't escape. And when that happens, then you've created a black hole. And so a black hole forms at the core of the star. And when that happens, that's a bad thing for the star, right? It's not good to have something like having what amounts to a bottomless pit in the center of a star. So stuff starts spiraling in and falling into the black hole, and this produces jets that go blowing out the poles of the star, and those jets basically blow a hole in the star, and they are so energetic that if you were looking at them as they come towards you, they appear as gamma rays. And so we call that a gamma ray burst. Gamma ray bursts are really bad things. You don't want to actually see one of them nearby. They can. It's been estimated that if a gamma ray burst were actually pointed right at us, anywhere in our part of the galaxy, um, it could take out life on Earth. It's that scary a thing. Um, they're very rare. You have to be lined up just right for that to happen. It hasn't happened in the 4.5 billion year history of the Earth, so it's not like it's a common thing. It's not like you have to worry about it a lot. But it's a measure of the energy of one of these things, that they really are that destructive. So gamma ray bursts are the sign of a black hole forming. And so when you see one of those, you are seeing the birth of a black hole. Black holes are are these compact objects. Even long after the gamma ray burst is done, the stuff isn't there. You can have this black hole, this dense lump of matter that is that stuff falls into and can't come out of. And a black hole is a very hard thing to observe. And so one of the things that we talked about right near the end of this section was, how do you observe a black hole? And there's a couple of different ways of doing it. In fact, there's a few now. There is one thing you can do is look for X-rays, because it turns out that as matter is falling into the black hole before it actually gets inside into the event horizon, um, it gets really, really hot and it produces X-rays. And so looking for X-rays can be a sign that stuff is falling into a black hole. And that's one of the ways that we can find black holes, is to look for that kind of thing. Another way to observe a black hole is to look for something that is orbiting around an unseen companion. Now, unseen may just mean it's a lot fainter. So the unseen companion could be a white dwarf. It could be a neutron star. It could be a black hole. It might even be just a low mass star, an ordinary main sequence low mass star. If it's a lot fainter than the brighter star, you might not see that. Okay, but if that unseen companion has a lot of mass, and we know it would have a lot of mass because we could see this other thing going around it, so we can measure the mass of the thing it's orbiting. And so we say, hey, there's a high mass star around it that's not producing not producing enough light to be seen. That would be a candidate for a black hole. And so we had a your turn question where that was basically the result. And I know some folks got some funny information on that one. There is no upper limit to the masses of black holes. So make sure you understand that, right? There is the minimum mass is about three solar masses, we think, although there may be ways of making smaller ones. But there isn't an upper limit. And in fact, later in the course, we'll be looking at black holes that are 1 billion solar masses. So yeah, don't assume that something could be too big to be a black hole. So that's these are the types of the ways that stars can end their lives. They can go through either that low mass star route and become a white dwarf and form a planetary nebula, and say that's the kind of quiet retirement approach. There's the supernova approach, the going out with a bang, where where those high mass stars blow off most of their mass and leave behind a neutron star like this one. Or there's the go out with a bang and take as many people with you as you can, the form a gamma ray burst approach, which is really takes which is what those stars over 25 solar mass do, where they blow away a large part of their mass but leave behind a black hole that can continue to be there in the universe. And if you're not really close to a black hole, it's just that much mass, and so there's stuff can orbit around it. It's just a lot of mass. It's just you can't see it. All right, So that's really what we've covered here. That's the phases, the different topics we've looked at since the last exam. I want to remind you the best way to prepare for one of these exams is to practice. Okay, I said it before. Practice quizzes, practice uh, the discussion questions, practice the your turn and the constellation questions. The more of that you do, the better shape you're going to be when you see one of those questions show up on the exam. Um, I'll continue to have my office hours as usual. So if you have any questions, just let me know. Good luck on the exam, and don't forget, we do have our quiz and discussion on just later in the week this week.